Alright, the very last thing that we're going to talk about in dynamics is we're going to talk about equilibrium. Equilibrium is a little bit of a more challenging topic, but we'll take it pretty slow. So when we're talking about something being in equilibrium, that's a really nice fancy physics way of just saying the net force on the object is zero. Or we could also say that the object's stationary. For those of you that do a little bit of physics at the post-secondary level, you'll also talk about the net torque on the object being zero when you're in equilibrium, but that's not really relevant to us in Physics 20 just because we don't study torque in Physics 20 nor Physics 30, sadly. So a lot of questions with equilibrium, they're going to deal with the force of tension, and most likely it's going to deal with you needing to actually calculate that force of tension. And we always remember that tension is directed away from the object. These questions, they're a little bit tricky, and sometimes they require you to do a lot of math, but I'm going to show you some special cases. There's a couple certain problems you can do them in a bit of a special way to cut down on the algebra, but it's also a very limited trick. But I'll show you those in another video. So a lot of times you may be asked to determine, or not a lot of times, sometimes you may be asked to determine this force called the equilibrant. So the equilibrant, it's a force that's exactly equal in magnitude, but it's opposite in direction to the net force. Basically, the gist of the equilibrant, if you add it to the net force, it should give you an overall force of zero. So F net plus F I'm not going to write out equilibrant, their sum should be equal to zero. If you know the net force, getting the equilibrant's really easy, and I'll show you that in this example right here. Trust me, you don't have to do any real additional work. So we got two forces of 30 newtons west and 20 newtons north pulling on an object. So we want to determine the resultant force, and we're going to determine the equilibrant. Well, for the resultant, this is just standard question. So we get our lovely little free body diagram. So I have a force of 20 newtons to the north. I'll call that F2 since it's the second one that was mentioned. And we also have this 30 newtons to the west here. So I'll call that F1 since it was the first one mentioned. So those are my two forces. Of course, we can also draw a vector diagram because we could show those two forces added together, the whole tip to tail. So again, as I've mentioned, from my years of taking Physics 20, I always draw my x vector first. It's just what my physics teacher taught me. No reason why we can't do it that way. Just what Mr. Estabrooks asked us to do. So I will follow that, but you don't have to. It's just I'm so hardwired on that. And then we'll draw... sorry, I got ahead of myself. I thought this was going to go south. I don't know why I thought that. Sorry, I got to give myself a bit more space. So there's F1. And then we're going to draw F2 right there. So the tail of F2 is going to go at the tip of the previous vector. So we're going to have F2. And then, of course, the resultant force. What color should we... let's give it a nice pink hue. So this is going to be my resultant force, a.k.a. the net force. So again, with my two components being at right angles, this is going to make some very nice, quick work. So I can get my net force's magnitude using Pythagorean theorem, and then that angle we'll get using SOHCAHTOA. So let's see here. So the magnitude of my net force, that is going to be the magnitude of F1 squared plus the magnitude of F2 squared, all square rooted. So we're going to have 30 newtons squared plus 20 newtons squared, all square rooted. Apologies for the messy writing. I've never had good writing, and I've tried to improve it over the years, and I've had zero luck on that one. So with sig digs, I'm going to say that that's 36 newtons. Now for my angle, I know my opposite side, F2. I know my adjacent side, F1. So for the angle, I know I can just take the inverse tangent of F2 over F1. So that's going to be the inverse tangent of 20 newtons divided by 30 newtons, which is going to give me, what is the inverse tangent of 2/3? About 34 degrees. And then for direction, I'm starting in the west direction and I'm starting to rotate up towards north. So I'm going to say that this is 34 degrees north of west. So the last little bit we do here, like I always like to do, I always like to marriage together my magnitude and my direction. So I could say for this lovely thing, my net force, it's equal to 36 newtons. and then 34 degrees north of west. So that's the magnitude of my net force acting on the object. To get the equilibrant force, you don't actually have to do a lot of work. It's going to have the same magnitude, it's just going to be opposite in direction. So all we have to do for the equilibrant force is change directions. So anywhere in your direction where you see a north, it's going to become a south, vice versa, south becomes a north. Anything that was an east becomes a west, and vice versa. Anything that's west that becomes an east. That's all you have to change in your net force. You don't have to change any of the numbers. The numbers, you leave them alone. You just change the direction. You're basically flipping it to the opposite direction. So in this 36 newtons, 34 degrees north of west, I'm just playing around with the north and the west. That north will become a south. That west is going to become an east. So I could say that my equilibrant force, wish there was a shorter notation for that. So the equilibrant force, same magnitude, same angle, but this time we're just going to have south of east. All we're doing for the equilibrant is changing the directions. You don't have to do any math or anything fancy. Just change the directions to the opposite direction, the one that's going 180. So north to south, south to north, east to west, west to east. No extra math required.